Okay, so these two questions here, let's just quickly talk through them. These ones, abstract, I don't think they're as abstract as the ones that we've just done in the examples, particularly that last one. These are still ones where there's just 9 elements. So I'm kind of, thinking, I'm looking and I'm thinking, oh, is it a nonagon? Is it rotations of the nonagon? In fact, of course it is, because no, it might not be. I was thinking that 9 was prime, and so there was only one isomorphism class. However, 9 is not prime. So it may be rotations of the nonagon, or it may not be. Distinct elements P and Q, both of which have order 3. So you can imagine that this could well have been written like this. Q cubed is equal to E. And then it's a commutative group. Now this is very nice because it's a commutative group. That's telling you that PQ is equal to QP. And in fact also P squared Q squared will be equal to Q squared P squared. And why haven't I written PQ squared? I guess because I don't need to, because it's told me that it's commutative. So what's the other one I haven't done? P squared Q is equal to QP squared. It's also telling me that P isn't equal to Q, rather isn't equal to P squared, because then I'd be able to write that just in terms of P alone. So it says just write down the elements of a proper subgroup, but I mean all of the elements would be the powers of P, but not PQ because that's E, the powers of Q, and then we could have a product of P and Q, but PQ is the same as QP, so let's just go with the P's first. And then I could have a P with Q squared, or I could have a P squared with Q squared, and I think that's it. 1, 2, 3, 4, 5, 6, 7, 8. I've missed one. What have I missed? I've missed P squared with Q. So those are our elements. Write down the elements of a proper subgroup of G, which doesn't contain Q. Well, okay, it's just those, isn't it? And which doesn't contain P, so that's going to be E, Q and Q squared. So that's easy enough. Find the order of each of the elements PQ and PQ squared. So that word justify, what do they mean? Well, I think it means that you need to do a little bit more work than possibly you would want to. So it's a group of order 9. So by one of those kind of little additions to Lagrange's theorem, you know that the subgroups can only have order that's a factor of 9, so 1, 3 or 9. Proper subgroups just order 3, but actually it's the same for the order of the elements, isn't it? So the order of the elements can only be 1, 3 or 9. So I'm thinking the order here is going to be 3. But justify my answers, I am going to work this out because I'm not exactly sure what that means. I'm not sure how the exam mark scheme will be allocating these. So PQ all squared is PQ times PQ. I am going to use the associative property, PQ. I'm going to write that down. Sorry, I'm using abbreviation there. They're very long words, aren't they? Now, what I'm going to do is I'm going to switch those two around. I can't normally do that in groups, but I can here because it's a commutative group. So by commutativity. And then I can say P times P is P squared, Q times Q is Q squared, and again I'm using associativity there. And that's it. Kind of stuck there, so that doesn't equal anything else. But I wasn't expecting it to. I'm expecting PQ cubed to be equal to E. So PQ cubed is the answer to PQ squared multiplied by PQ. I'm going to use associativity there. I'm now going to switch those around, and you can see we're there, because switching those two around by the commutative property gets me p cubed, q cubed, which is equal to e. And that, of course, is just by definition or by the facts that I was told that at the start. Was I told that? Well, I was told they've got order 3, so you might want to put order 3 rather than that. Now we've got to do the same for pq squared, pq squared, squared, pq squared, pq squared, associativity, switch those around, p squared q to the 4, which is p squared q. So what I've done there, I of course haven't written the things down. You would need to write the things down. pq squared cubed then is equal to pq squared squared multiplied by pq squared. That first bit is equal to p squared q, and pq squared. Use commutativity, I guess associativity first, and then switch those around in the middle. P squared pqq squared, that's going to be p cubed q cubed, which is equal to e. Write down associativity, commutativity when you have used it there, because the order of p and the order of q is equal to 3. State the possible orders of proper subgroups. Okay, it says state. Can we just write down 3? State implies just an answer, doesn't it? If it said determine, I'd possibly do it a little bit more. I think just anyway, I would be a bit nervous, and I would say the factors of 9 are 1, 3 and 9. So by Lagrange's theorem, the factors of any subgroup are 1, 3 and 9. Proper subgroups will have order 3. So I think I would do that myself, certainly if it was an exam question. And then D, this is quite interesting. Find 2 proper subgroups of G which are distinct from those in part A, simplifying the elements. You might think, oh gosh, do I have to do a group table? You might think, well, should I just find the orders of some elements? But I think exam questions, I know examiners are horrible, but sometimes they can be helpful. We had to do quite a little bit of work, didn't we, in B? If I've got a subgroup that's got order 3, I need the order of the elements to be 3. If I've got PQ, and if I square it, I get P squared Q squared. If I were then to multiply these two together, of course, that gets me P cubed, Q cubed, which is equal to E. It seems as if E, PQ, and P squared, Q squared might well form a group. And I say might well, I mean, no, of course they do, because that times that gets me that times that gets me that times that would get me P to the 4, Q to the 4, which is PQ. So there I've got one group. Okay, so have they been helpful for a second time? If we look at this here, if I have PQ squared, if I square that, I get P squared Q. I know that multiplying P squared Q by P squared Q, it gets me back to the identity. I know that multiplying that one by itself will get P squared Q to the power 4, which is equal to that. I know that that multiplied by itself is P to the 4 Q squared, which is that. And of course, multiplying those together gets P cubed Q cubed, which is equal to E. So there's my other one. There could well be more. However, that is all that we need. So, is it a nonagon? I don't think it is a nonagon, is it? Because we are not going to have any element there with order 9. So there's going to be no generators that is not a cyclic group. Okay, question 17. Do I have time? Or more importantly, do I have space before I run out of space on my phone? Now, multiplicative group of order 12. I mean, note that both these questions here are bigger than 7. Obviously, they're bigger than 7, but in the isomorphic table, you have to know those groups really, really well. You are asked here about a group of order 9 and a group of order 12, but then the actual questions are asking you about subgroups. So you're given a larger group, but you have to think about orders of elements, but subgroups you're looking at are from the 1 to 7 that you're supposed to know about and do, of course, know about really well. So this one here, it is given that R has got order 6. So if R has got order 6, R to the 6 is equal to E. We also know that A squared is R cubed. So if I think about how I can use that, I then know that if I square both of those, that gets me the identity, because R to the 6 is equal to E. So I know that the order of A is equal to 4. That makes sense because I know a group of order 12, I'm looking at order of elements being 2, 3, 4 and 6. They've got to be factors, of course, 1 and 12 as well. Find the orders of these. Well, I can just write those down. The order of A is 4, as A to the 4 is equal to E. A squared has got order 2, as A squared all squared is equal to E. And A cubed has order, well, if you think about multiples, 3, 6, 9, 12. There you go. That is the first power that is a multiple of 4. Oh, and R squared has order, so R squared to what power gives you E? Of course it's cubed, isn't it? Okay, you've got to read this carefully. The table shows the number of elements of Q with each possible order. Okay, so in your group of order 12, you've obviously got the identity, you've got one self-inverse, a couple of paired inverses, you've got 6 elements of order 4, and then 2 elements of order 6. So you know what I'm thinking. I'm thinking symmetry, aren't I? I'm thinking, could it be rotations of a dodecagon? Okay, well, no, it can't. It's not a cyclic group. There are no elements of order 12. So then I'm thinking, it might be rotations of a hexagon. If it was rotations of a hexagon, there would be an awful lot of elements that were self-inverses. So in fact, you'd have 6, wouldn't you? No, 7. So I would have a reflection, a reflection, a reflection, and then a reflection, a reflection. Oh, I've missed one. Where's the other one? I think I just missed there. So I'm going to have 6 reflections, and then I'm going to have the 1. So I'd actually have 7 self-inverses. So it's nothing to do with symmetries, which makes me sad. But we can use symmetries in the next part. G and H are the non-cyclic groups of order 4 and 6. Now, when I first kind of did this, I was looking and trying to get them into there. It's not talking about subgroups. It's just talking about the non-cyclic groups. You know that there are 2 classes of groups of order 4. One is the cyclic one, which is isomorphic to our rotations of the square. The non-cyclic group, it's called the Klein group. It's the one that's the symmetries of the rectangle. So the order of elements, we can have 1, 2 and 4, and the number of elements, well, we've got the identity there. We have got, they are all order 2, aren't they? So we've got the reflection in that axis, the reflection in that axis, and then our rotation. So that is G. Now, if we look at H, you've got 2 classes of isomorphisms. Order 6, you've got the rotations of the hexagon, and you've got the reflective symmetries, sorry, not just reflective, all symmetries of the equilateral triangle. It's called D3. Factors of 6 are 1, 2, 3 and 6. I've got my inverse, not my inverse, my identity there. Order 2, reflection there, reflection there, reflection there. Okay, I don't have a rotation on order 2 because, of course, it's got 3 sides. It's going to be 120, 240 back to the start. So I'm going to have 3 there. 1, there's 4, so there's going to be 2. Yeah, there's the 240 rotation as well as the 120 rotation. And there are no elements of order 6. Neither of these are cyclic. I know that, they're non-cyclic. So those are my group tables. Hence explain why there are no non-cyclic proper subgroups of Q. Okay, so we would know that firstly we've got a group of order 12. So the proper subgroups, order 12, by Lagrange's theorem. Sorry, this is a very odd sentence structure, isn't it? Have order 2, 3, 4, and 6. So I think I would say factors of 12 are 2, 3, 4, and 6. So by Lagrange's theorem, the orders of the proper subgroups would be 2, 3, 4, and 6, or something. Right, I can immediately discount these two. So as 2 and 3 are prime, these would be cyclic. Okay, I'm not sure why I've done that. Why have I done that? To show the number of elements, explain why there are no non-cyclic proper subgroups. Okay, I've lost my thread here. Why any group order 2 and 3 is cyclic. Oh, okay. So, yeah, I'm asked to explain why there's no non-cyclic. Okay. So, there could well be a group of order 2, but it's going to be cyclic. Okay. So, not non-cyclic. Apologies. I was so slow there. Right. Okay. So, if we look at order 4, we know here that order 4, and in fact, shall we do them together? Order 6 as well. So, any non-cyclic subgroup of order 4 or 6 must have 3 elements of order 2. Our group here, what is it? Q has only one subgroup, order 2. So there can be no non-cyclic groups, order 4 or 6, or none of any order. Now, you might think, why has she written that? You can't read it, I'm sure, with my scroll. But you need to write these things down. Okay, so I did think, well, should I just kind of say it? But you need to kind of look at these model answers. I know it's obvious, but you need to tie together that argument at the end. So not just say, well, it's obvious because of this. The examiner isn't going to know that you know all the theory or that you remember all the theory. So please, 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 it's important to get it down. Okay, I hope those questions were okay. I hope that the questions that I'm going to give you now, I think there are about 10 or so, don't worry, just get stuck in. You don't have to email me next week. I mean, shall we just say, the start of next term? I wouldn't, though, let that give you an excuse to kind of put it off to the last week of term. Please do, start in the next couple of weeks. Okay, I will see you in September. Very excitingly, new topic. I wonder what we'll do. It could be mechanics or a bit of vectors. I'm just looking. If you've done enough calculus, we could go on to some differentiation, which might be fun. Anyway, I'll see you September.